Today we continue to do a few more examples on magnetism. This is an important question in which we are asked to determine the magnetic ground state the G value of this ground state and the corresponding magnetic moment for all 3D and 4F ions. Some of these results we have already used in our discussion of the basic ideas of magnetism in solids, but today we will work out the magnetic ground state, the corresponding G value and the magnetic moment in the case of all the members of the 3D and 4F groups in the periodic table. We will consider the 4F first for reasons which will become obvious very soon. 4F ions, which are better known as, more commonly known as rare earth ions. The rare earth ions are a group of elements in the periodic table which correspond to the successive filling up of the 4F shell. The 4F shell corresponds to an angular momentum of 3. So, the electronic configuration is such that the outermost shell is or the 4F and then phi s, phi p and in some cases phi d shells. So, these are the outer electron configurations. There are of course closed shells inside which do not contribute anything to the magnetic moment. It is only the unpaired electrons in the unfilled shell which give rise to magnetic moment. So, we have the possibility, since L is 3, we have ML going from -3 to +3 in integral steps. So, this corresponds to 7. And then there is a spin which can be plus or minus half. So, there are 2 orientations. So, there are 14 electronic states. 14 electrons can occupy the 4F shell. So, corresponding to 4F0 where there are no electrons in the 4F shell, and then 4F1, 4F2 etc., 4F14. All the elements corresponding to these different values of the electron in the 4F shell form the so called rare earth group. We will consider one by one these elements, and the reason why we consider this first rather than the 3D is because in the 4F group there are outer electrons in the phi s, phi p and phi d shells which sort of shield the inner 4F electron. The spin orbit coupling is relatively strong in comparison to the crystal field effect. So, the spin orbit coupling is rather strong, and therefore, if we wrote the free electron Hamiltonian, we have the single electron states corresponding to the kinetic energy, where I is going from 1 to the total number plus V of R I. This is the kinetic energy, this is the potential energy, the Coulomb interaction energy between the ith electron and the nucleus. So, this is all single electron terms. These define the angular momentum and spin of every individual electron. In addition, next in descending order of strength, we have the inter-electron Coulomb repulsion. This is a 2 electron term. So, this couples the individual electrons, and in the Hartree approximation considers the spherical part of this inter-electron repulsion and adds this on to the single electron potential energy, so that we get a hydrogen like ground state, but there will be a non-spherical part. Coulomb repulsion. This non-spherical part of the Coulomb repulsive potential couples the individual L's and S's of the single electron and produce a total angular momentum, orbital angular momentum L, and a total spin angular momentum S. According to the rules of angular momentum coupling in quantum mechanics. It is these L's and S's which define the so called the spectroscopic terms. So, these spectroscopic terms are identified by the total value of the orbital angular momentum. If L is 0, we call it an S term. If L is 1, it is a P term. If L is 2, it is a D term. If L is 3, it is an F term, and then 4, 5, etc., it is in alphabetical order, G, etc., and so on. So, these are the term symbols corresponding to the different angular momentum values, orbital angular momentum values. Once we know the individual total orbital and spin angular momentum corresponding to the ground term, it is the ground state which matters in magnetic properties, and therefore, we are interested in the ground term, and this term now is acted on by the spin orbit coupling. Which is usually represented in the form lambda L dot S, where lambda is the spin orbit coupling constant. And this produces a coupling between the orbital and spin angular momenta to produce a total angular momentum, which is usually represented by the symbol J. Corresponding to a given value of J, you can have different values of Mj, the magnetic quantum number, which goes from minus J to plus J. There are 2J plus 1 values corresponding to different orientations of the spins. Magnetic moment of the ions with respect to an applied magnetic field. So, now these correspond to the so called multiplets. Different J values correspond to different multiplets. When L and S are coupled according to the rules of angular momentum coupling, it can be coupled and the resultant angular momentum goes from J equal to L plus S to mod L minus S or S minus L, depending on which is greater in integral steps. That is how we get 2J plus 1 values. Each of these J value corresponds to a different multiplet. So, this gives me the multiplet states spectroscopic multiplets. There are different multiplets corresponding to different values of J, of which the ground multiplet is what matters for magnetic behavior. So, the magnetic ground state is determined by the multiplet which lies lowest, on account of the fact that the excited states are normally not appreciably populated under ordinary conditions of temperature and magnetic field. So, it is only the ground multiplet which determines the magnetic ground state and hence the magnetic behavior. So, the magnetic ground state which we have been asked to determine corresponds to the ground multiplet state. This is what we have to determine now in the case of the different ions. Once we know the multiplet ground state and the corresponding J value, so we now know the L, S and J values for a given multiplet. A given multiplet is characterized by different values of L, S and J, and then the G factor, which is known as the Landé G factor, is given by corresponding to a given multiplet state with a given J value is given by the Landé expression. So, since we know L, S and J for a given multiplet characterized by a particular value of J, we can immediately find the corresponding G value. This is also what we have to find out. Once we know Gj, the magnetic moment of corresponding to this ground state, it is usually represented by the symbol P effective, which is in Bohr magnetons. So, this P effective is given by G j into j into j plus 1 to the power half. So, this gives the magnetic moment in units of the Bohr magneton. So, this is the procedure which we will adopt in the case of all the 14 rare earth ions belonging to the progressive filling up of the 4f shell. Well, if there are no electrons in the 4f shell, there is no magnetic moment obviously, because the shell is not occupied by any electron, and therefore, the unpaired electron is necessary for. So, let us start from the first case, first rare earth ion, which is cerium 3 plus, which has the outer electron configuration of 4f1, 5s2 and 5p6. So, there are 2 electrons in the outer 5s shell and 6 electrons in the outer 5p shell, and there is one unpaired electron in the 4f shell. So, it is this which gives the magnetic behavior. So, since there we have only one electron, the L value is, since it is an electron in the f shell, L is 3, and since there is only one electron, the spin value is also, the total spin angular momentum is just that of one electron. So, S is half. So, you have J, which in this case the low lying multiplet corresponds to L minus S rather than L plus S, because the 4f shell is less than half filled. So, this is the ground multiplet. So, in this case, since L is 3 and S is half, this will give you 5 by 2. So, the ground multiplet has L equal to 3, S equal to half, and J is 5 by 2. There is a way of denoting this ground multiplet. The spectroscopic notation for this ground multiplet usually proceeds by giving the ground term symbol, which we already saw. In this case, since L is 3, it is an F term, and it has a superscript which has the spin degeneracy, and the subscript which gives the J value. So, that is the standard notation for the ground multiplet. In this case, the spin degeneracy is for a spin of S, spin degeneracy is 2s plus 1 obviously. So, we will have in this case S is half. So, 2s plus 1 is 2. So, it is 2f and the J value is 5 by 2. So, that is the notation for the ground multiplet for the cerium 3 plus ion. which is the first member in the rare earth group with unpaired electron. So, having found the ground multiplet, we use the expression for the Landé G factor to find Gj, the G factor corresponding to this multiplet. So, this has L equal to 3, S equal to half, and J is 5 by 2. So, the Landé expression is for Gj is 1 plus j into j plus 1, which is 5 by 2 into 7 by 2 plus s into s plus 1, which is half into 3 by 2 minus L into L plus 1, which is 3 into 4 divided by 2j into j plus 1. This turns out to be 2.958 on simplification. The corresponding magnetic moment is given by this formula. So, we write P effective is this value for Gj times 5 by 2 j into j plus 1 to the power half. So, this turns out to be 2.54 Bohr magnetons. So, following the same procedure for the other ions, let us move on to the next ion in the rare earth group, which has 2 electrons in the 4f shell. This ion is praseodymium 3 plus. So, it has 4f2. And therefore, the corresponding L value is there are 2 electrons. The Hund's rules tells you if I have different values of ML, which I represent here. So, this is ML equal to -3, -2, -1, 0, 1, 2 and 3 corresponding to L equal to 3. So, the Hund's rules tells us that the electrons will have a total ML value and hence a total L value due to the coupling, which will correspond to the sum of the 2 states which the electron occupies, the corresponding ML values sigma ML corresponding to the 2 states, such that the spin multiplicity is maximum. In other words, the 2 electrons have spins parallel. So, these are the 2 states, and therefore, we get -5, or it can also be here. So, it is plus or minus 5, and therefore, the corresponding L value is 5, since this summation is gives you ML as plus or minus 5. The only possibility for this is with L equal to 5. So, that is the total orbital angular momentum of these 2 electrons, and since there are 2 electrons, the spins are parallel, and therefore, S is 1, and J, which is mod of L minus S, because it is still less than half filled. So, this will be 5 minus 1, 4. So, the ground multiplet in the case of the praseodymium 3 plus ion has the L value 5, which means it is an H term, and the spin multiplicity is 2s plus 1 for s equal to 1 is 3, and the J value is 4. And if we substitute in the Landé G factor expression for this, the Gj turns out to be 4 by 5. by substitution, and the corresponding effective magnetic moment is 3.58 Bohr magnetrons. Adopting the same procedure for the next ion in the series, which is neodymium 3 plus, which has 3 electrons in the 4f shell, and therefore, following the same procedure, sigma ml will be -3, -2 and -1. So, this will be -6. So, L will be 6, and the S, since there are 3 electrons all with spin parallel in order to maximize the spin. So, this will be 3/2, and therefore, J will be L minus S, which is 9/2. So, the ground multiplet for neodymium 3 plus is L equal to 6, which is an I term, 2s plus 1 is 4 for S equal to 3/2, and the J is 9/2. So, this is the ground multiplet. All the rare earth ions have the valency 3 plus. The corresponding Gj value in the Landé G factor expression works out to be 8/11. And the effective magnetic moment P effective is 3.62 Bohr magnetons. We then move on to promethium 3 plus, which is a short lived isotope. Still it is one with 4 electrons in the 4f shell. So, the corresponding L value, since this would be 4 electron, this would add 0 to this. So, the L remains 6, and the S of course becomes 2, since there are 4 electrons with parallel spins, and therefore, the J is 4. So, the ground multiplet is again an I term, but with spin multiplicity 5, 2s plus 1 for S equal to 2, and the J value is 4. Next we consider samarium 3 plus, which has a 4f5 configuration. Therefore, the L, now there are 5 electrons. So, the -1 and +1 will neutralize each other, leaving us with sigma ml equal to -5. So, that L is 5, and S for 5 electrons is still 5/2, because all the electrons have parallel spins. Therefore, the J value is L minus S, which is 5/2, and the Gj has the value, the ground multiplet is represented by L equal to 5. So, it is again an H term with spin multiplicity 6 corresponding to a spin of 5/2 and J value of 5/2. This is the ground multiplet. And the corresponding Gj value is 2/7. And the magnetic moment is having the value 0.84 Bohr magnetons. We go to europium 3 plus, which has 6 electrons in 4f shell. So, L is 3 by the same procedure, S is also 3 because 6 electrons with parallel spins, and so J is 0. So, the ground multiplet is an F term with spin multiplicity 7 and a J value of 0. So, since this has J is 0, so the G value is 0 and the magnetic moment corresponding to that is also 0. Of course, europium 3 plus is non-magnetic because of this, but usually europium 3 plus also there is frequently you have a mixed valence with europium 2 plus, which contributes to some non-zero magnetism. When europium 2 plus is present. Next we have gadolinium 3 plus, which has 7 electrons in the 4f shell, which can accommodate a total of 14 electrons. So, this is a half filled shell. The corresponding L value turns out to be 0, S is 7 by 2 and J is also 7 by 2. Since L is 0, the ground multiplet has a term symbol which is that of an S term, and therefore, this will be 8S 7 by 2. So, substituting these values of Ls and J, we get Gj for gadolinium 3 plus as 2. It is just the spin only value. Since it has only spin contribution, the orbital angular momentum is 0. So, it has a spin only G factor, and the corresponding magnetic moment has the value of 7.94 Bohr magneton. In the same way, we can work out the values for the other 7 electrons. So, terbium 3 plus, which has 8 electrons in the 4f shell. So, L is 3, S is 3, J is 6. In this case, the S is 3 because there are 7 electrons with parallel spin, and then the 8th electron goes to this, so that you have plus 3 and minus 3 cancelling out, leaving L equal to 3. The corresponding Gj value, since it is more than half filled shell, the ground multiplet is corresponding to L equal to 3. It is an F term with the spin multiplicity of 7 and the J value of 6. The Gj value is 3 by 2 and the effective magnetic moment is 9.72 Bohr magnetons. Similarly, we consider dysprosium 3 plus, which has 4f9 configuration. The corresponding values are L equal to 5, S equal to 5 by 2 and J is 15 by 2. So, the ground multiplet is 6H 15 by 2 and the Gj value is 4 by 3. The magnetic moment is 10.63 Bohr magnetons. In the same way, one can verify the cases of holmium 3 plus, which has 4f10 and the L value is 6, S value is 2, J value is 8. So, the ground multiplet is 6. So, it is an I term with 5, 8. So, the Gj value is 5 by 4 in this case, and the magnetic moment is 10.6 Bohr magnetons. Then we have erbium 3 plus, which has 4f11, and the corresponding L value is 6, S is 3 by 2, J is 15 by 2. So, the ground multiplet is again an I term with 4, 15 by 2, leading to a Gj value of 6 by 5 and a P effective of 9.59 Bohr magnet. We next come to the case of thulium, which has 4f12. So, the L value is 5, S value is 1, J value is 6, and the ground multiplet is an H term with spin multiplicity 3 and J equal to 6. So, the Gj is 7 by 6 and the P effective is just 7.57 Bohr magnetons. Lastly, we have ytterbium 3 plus, which has 13 electrons in the 4f shell, and the corresponding values of L, S, J are L equal to 3, S equal to half, J equal to 7 by 2, and the ground multiplet is F term because L is 3, 2, 7 by 2. So, Gj is 8 by 7 and P effective is 4.24 Bohr magnetons. We of course have the final case of lutetium, which has the full shell filled with all the 14 electrons. So, this corresponds to L equal to 0, S equal to 0, J equal to 0, because it is a closed shell, and therefore, it is diamagnetic, no paramagnetism, no unpaired electrons. So, that completes the story about the rare earth ions. We now move on to the ion group or 3D group ions, the ion group ion corresponding to the progressive filling up of the 3D shell. In this case, the spin orbit coupling is weaker than crystal field splitting, because there is a crystalline electric field and the 3D ions which lie outermost, there are no outer electrons shielding them. So, they lie outermost and therefore, they experience the effect of the crystal field, and therefore, the crystal field splitting is much stronger than the spin orbit coupling. So, one has to determine the crystal field split ground term. Usually, the crystal field is so strong that the orbital angular momentum is completely quenched. Therefore, the only angular momentum which contributes to magnetism is the spin angular momentum. So, it is spin only magnetism. So, the G factor is that of the spin value, pure spin value 2, close to 2, and the corresponding magnetic moment is 2 s into s plus 1 to the power half, where s is the spin angular momentum. So, with this prescription, let us look at the ions in the 3D shell. So, we start with titanium 3 plus, which has 3D1, 1 electron. So, it has, since it is a d electron, the ground term has the symbol d, and it is a 2D term, which is the ground term. Therefore, 2 s into s plus 1 to the power half in this case is 2 into half into 3 by 2 to the power half. This is the value of the effective magnetic moment. This is the G value. So, this works out to be 1.73. Then we have V4 plus vanadium, which has also 3D1. So, its behavior is similar. Then vanadium 3 plus has 2 electrons, 3D2, and that corresponds to a 3F by the same reasoning as we did for the rare earth ions, and the P effective in this case is 2.8. We can also have vanadium 2 plus, which is 3D3, and the spectroscopic ground term is 4F, and the P effective will be 3.87, 2.83 here. Vanadium 2 plus as well as chromium 3 plus and manganese 4 plus all have the same electronic configuration of 3D3, and so they have similar magnetic behavior. Then we move on to manganese 3 plus, which has 4 electrons in the 3D shell, and therefore, it has a phi d term giving a magnetic moment of 4.9 Bohr magnet. Then Mn 2 plus, which has 5 electrons, so it is a half filled shell with a spectroscopic ground term of 6s. It is an S state, and so the P effective, since it is an S state, so it will be 5.92. This is also the case with iron 3 plus. It is identical, isoelectronic. Then we go on to ferrous ion, which has 3D6 configuration, and again a phi d ground term with a magnetic moment, calculated magnetic moment of 4.9 as before. Then we have cobalt 2 plus, which is 3D7 and a 4F ground term, P effective of 3.87. Then we have nickel 2 plus, which is 3D8, and so a 3F ground term and a magnetic moment of 2.83. Finally, we come to copper 2 plus cuprous ion which has a 3d9 configuration. So, it has a 2d ground term with the P effective of 1.73 Bohr magnetron. So, the experimental measured magnetic moments are given in the last column in this table. So, we can see that the agreement with the spin only magnetic moment is fairly good. Next, we are asked to calculate the molar magnetic entropy. Of an assembly of non-interacting paramagnetic ions molar means the number of spins is the Avogadro number. Each of these has a total angular momentum of J and a magnetic field is applied. So, if you have a total angular momentum of J, there are 2J plus 1 orientations possible for each ion with respect to the direction of the applied magnetic field. Therefore, the magnetic entropy can be calculated readily from the Boltzmann formula, which gives the magnetic entropy as Kb log W, where Kb is the Boltzmann constant and W is the number of different configurations. So, this will be in this case, since there are n ions, Na, where Na is the Avogadro number, and therefore, the total probability is Kb log 2J plus 1 to the power Na. And therefore, since it is logarithm, it will be and we know that Kb Na is just the universal gas constant R, and therefore, it is R log 2J plus 1. So, this is the magnetic entropy that is available in a system of paramagnetic ions and in an applied magnetic field. So, you can have the technique of adiabatic demagnetization by means of which we can remove the applied magnetic field suddenly, keeping the spins in thermal isolation, and this entropy causes a cooling of the spins or the paramagnetic ions by this technique, which takes these to very low temperatures. This technique has been used to achieve extremely low temperatures. It is a refrigeration technique.